Molecules and compounds are the subject matter for this week. I want to begin with a review of water. I showed you before that water has a formula of H2O. This means we have 2 hydrogen atoms for every 1 oxygen atom. Please excuse the typos. Since hydrogen atoms have an atomic mass of 1 and oxygen atoms have an atomic mass of 16, then water has an atomic mass of 18. So what we can do is we can start to look at this in terms of how water plays out in terms of the number of moles and stuff like this. Remember, we did this with CO2. So water looks like this, where we have an H, O, H. This HOH is this H2O. This thing has 1 AMU. This one has 16 AMUs. This one has 1 AMU. When we add all that stuff up together, we get 18 AMUs. The problem is we cannot weigh an AMU. But if we take this and we call it grams, now we can measure 18 grams, right? We can measure that mass fairly well. We can also relate this 18 grams to a mole, remember? So we can say if we've got 18 grams of water, that's going to equal to 1 mole of water, which is equal to 6.02 times 10 to the 23rd molecules of water. Now, that is an important thing, because now then, if I have an H2O and it's going to react with some compound X, and I don't know what X is, we'll just say it's X. If it reacts with this, then that means 1 molecule of H2O, because we have an understood 1 right here, right? Reacts with 1 molecule of X. So if I've got Avogadro's number of molecules, then that means I have Avogadro's number of H2O is going to react with Avogadro's number of X's. So now then we can start to predict how much reaction, not just what kind of reaction, but how much reaction will actually happen. So this, it becomes pretty important. When we look at something else with regard to, say, table salt, that's kind of interesting. We can do something exactly identical. So what we can do is we can basically say, well, we know that we've got 1 sodium and 1 chlorine, okay? So sodium weighs this 23 AMUs. Chlorine weighs 35.5 AMUs, and when we put it all together, what do we get? Not bibbidi-bobbidi-boo, we get 58.5 AMUs. This here, this 58.5 AMUs is for NaCl. Now, this, recall, is salt, just your regular table salt. Remember, though, what happens is that chlorine steals that sodium's 1 electron, and now then we've got a chlorine that's negatively charged, and we've got a sodium that's positively charged for this table salt. So what we do is we call, when we convert this 58.5 AMUs to 58.5 grams, now then we have 58.5 grams of something called a formula unit. It's a fancy way of saying positives and negatives that are stuck together. Okay? This is a little different than what we talked about for water. when we have water and you've got this H2O, right? They actually share electrons one to another. Because remember, water actually looks like this, right? So if water looks like this, and we're sharing a couple of electrons here and a couple of electrons here, now then, because of the sharing, we call this a molecule. And when we look at the 18 grams, that becomes the molecular, because it's a molecular mass. For sodium chloride, now we, instead of calling, because it's a formula unit, this 58.5 is its formula mass. So for things that have a positive and a negative charge, because those electrons are kind of stripped from one and added to another, those are formula units. So this right here is a formula unit, and the mass that it has is its formula mass. So compounds are kind of an interesting thing. We can classify things in all sorts of different ways. So the way that I kind of work through this, I say we have compounds, COMLBS is compounds, right? We can categorize them in two different ways. We can categorize them as molecules, like water, or we can categorize them as formula units, like salt. These are two different things that we can categorize pretty interestingly. So what makes these different are how the electrons are passed one between another. So what we find is when you have this with the sodium chloride, we actually have something kind of interesting here. We have an Na plus, this bound to a Cl minus, right? So Na plus is a cation, is how it's pronounced. So it's pronounced cat and then ion. And Cl minus is called an anion. I kind of remember these things because this T right here in the middle kind of looks like a big plus, doesn't it? So cations are positively charged, anions are negatively charged, hence the N in the middle maybe. So we know that we have, when one cation grabs one anion, now then when you put those things together, because nature likes to neutralize charge just like a lightning strike, together they are a formula unit. Now, you don't just have to have an Na plus and a Cl minus. You can do all sorts of different things. Magnesium is right next to sodium. Magnesium has to lose 2 electrons, and when it loses 2 electrons, it becomes Mg2+. Well, what if I have 2 chlorides? This here becomes another type of formula unit, just like this one did. So sodium chloride is salt. Magnesium chloride is a different kind of salt. So we can write these things as NaCl or MgCl2. Notice that we have anions and cations that are bound one to another. These are formula units. The reason why these formula units combine like this, go back to what we talked about with regard to the octet rule. Sodium needs to lose an electron to look like the nearest noble gas. Chlorine needs to grab an electron to look like its nearest noble gas. And together they form a formula unit where sodium's plus and chlorine's minus. Magnesium has to lose 2 electrons to look like the nearest noble gas, because it's kind of ridiculous to think of it gaining 6 electrons, right? Chlorine still needs to gain an electron to look like a noble gas, but because chlorine can only gain 1 electron, you need 2 chlorines that each gain 1 electron from that magnesium to become magnesium chloride. So now then we can start to think about these ionic versus covalent compounds. This is kind of an interesting thing. So an ionic compound are these formula units. Ionic compounds have a metal bound to a nonmetal. Covalent are a couple of nonmetals together. So let's look at an ionic compound. Remember, I showed you Na with an X and a plus a Cl with all these little dots around it, right? Whenever you react them together, now then that Na becomes positively charged, and the chlorine with its little dots around grabs that extra electron using the Lewis dot structures and becomes negatively charged. This positive charge and this negative charge have to stay close to one another, because if they don't, well, we start to have a charge imbalance, which is going to mess things up. So think of it this way. Chlorine steals sodium's sucker, but sodium still kind of follows chlorine around because chlorine has the sucker that it would like to have but doesn't have to have. Okay? With water, we have a couple, 2 of these H's, like this, will react with 1 oxygen that looks like this. But when this happens, we actually have an H that binds like so, and an H that binds like this. So now then we get this oxygen that's right here in the middle that has its 8 electrons, right? So it's perfectly content. But hydrogen, to look like the nearest noble gas, has to gain 1 electron. So when we look at the hydrogens, they look content too, because they got 2 electrons, which look like helium, the nearest noble gas. So now that we got this H, O, H that kind of looks like this. So think of this as kind of a handshake. Oxygen and hydrogen are shaking hands one with another, because that's still allowed for these atoms to do. But with the handshake going on, they're not going to rip a hand off. That's just awkward and doesn't deserve to be in this rated PG video. What's going to happen is they're just going to shake hands and tag along one with another. It's kind of like first grade. You kind of hold hands with your best friend. Not that big a deal, right? And you can wander through and skip them through the playground. So hydrogen and oxygen can hold hands and be perfectly content. And oxygen needs 2 electrons to look like the nearest noble gas, so it's going to find 2 hydrogens to do that with. Hydrogen is one of these nonmetals, just like oxygen is. So you have something that's kind of interesting. You have 2 different definitions. Let me go ahead and change this. You have ionic compounds, and you have covalent compounds. So these covalent compounds, covalent basically means something that is sharing 2 electrons. An ionic compound means you're going to have an unequal sharing and I really don't feel comfortable calling it a sharing because it's not really a sharing at all. You have an unequal distribution of electrons. So that means you're going to end up with a positive metal and a negative nonmetal or anion. So how's this going to play out? Now then we have ionic compounds, we have covalent compounds. Well, if we come back up here to this thing, we can look at different classifications again, right? So formula units, these are classified as ionic compounds. Molecules end up being classified as covalent compounds. So now we can start to look at all sorts of different things. So let's look at ionic compounds to begin with. Ionic compounds will have a metal that'll form a positive ion or a cation, and they will have a nonmetal that forms a negative ion. When we have our periodic chart of the elements, okay? I hope you enjoy my periodic chart of the elements. You've got this thing right here that looks like all this stuff right here. Those are our metals. Metals are always going to lose. They lose electrons. Okay? By definition, they lose electrons. You also have this thing over here on this other side, right here. These are non-metals. They are going to gain electrons. And they're all trying to look like something. What are they trying to look like? They're trying to look like these noble gases right here, right? So they need to look like these noble gases. And how do they do that? They got to find 8 electrons. And they put these 8 electrons in their outer shell, or their valence shell. So when we have a metal that's over here, it's going to lose 1 electron to look like something that's over here. When we have a nonmetal that's right here, it's going to lose 1 electron to look like something right here. Does that make sense? So this one will loop backwards to over here, and this one just goes right on over to the next place. That's how this kind of plays out. So let's see if we can figure out some of these things. So for instance, what happens with potassium and oxygen? Well, we know that potassium has 1 electron, right? So it needs to lose its 1 electron, right? So if we do minus 1 electron, what do we end up with? We get a potassium that has a positive charge. We have an oxygen over here that looks like this, right? So we need 2 electrons over here, don't we? So we need plus 2 electrons. When that happens, we end up with an O2 minus. Okay? So how are we going to take these 2 things and put them together? Well, you have to look at the charges. You have to balance those charges. If I have an oxygen that has a 2 minus charge, to get a potassium, if I just put a potassium next to it with 1 positive charge, that doesn't cancel out the charges, right? I still have a negative charge there, right? So I still end up with a negative charge. That ain't so good. So what if I put 2 potassiums here? So I have 2 potassiums, each with a positive charge. Now then, positive 2 plus a negative 2 is equal to a 0 charge. So now then I can start to see I can form these things called ionic compounds. These ionic compounds with different cations and anions end up being stuck in regular arrays or crystals. Have you ever noticed that a salt crystal is in a perfect cube? The reason for that is shown here, where we've got the sodium, which loses its 1 electron, and a chlorine, which gains that one electron. And you notice that we have each sodium is surrounded by 6 chlorines. And each chlorine is surrounded by 6 sodiums. So this allows us to balance out all the charges in a crystal structure. When we dissolve sodium chloride, it splits off into sodium ions and chlorine ions. So we kind of knock off one of these things and they hop into solution when you dissolve them. So now then, because we have positive and negative ions in solution, when you have ions in solution, and by solution I mean something that actually is a homogeneous mixture with something dissolved in it. When ions are in solution, we have something called an electrolyte solution. So as you know, in embalming, you have to maintain a good electrolyte balance. If you don't, sometimes one of the problems that happens is, and you see this a lot with patients who have been, or bodies who have been, patients who are deceased who died in the hospital and have had an IV fluids. If their electrolytes are not balanced, then you can have swelling of the tissues. So it's important to make sure that you balance the electrolytes. Otherwise, you end up with an unnatural look relative to what the family is used to seeing. Now, covalent compounds, because they share things, because they share valence electrons, they form covalent bonds. Now, how does this play out? Well, it's kind of like what I was telling you. What if I have something that's kind of interesting for y'all? That's something that's kind of interesting for y'all that's a covalent compound, has covalent bonds, would be formaldehyde. Formaldehyde is used in embalming and has the formula of CH2O. That's not H2O with carbon that's swimming around it with it. It's a little different. So what I want to do is kind of show you how to build this. When you look at the periodic chart, okay, and we're looking over here primarily, we have an H there. So now then we have this carbon here. We have an oxygen that's let me go ahead and expand this out. Well, that little part right there in the periodic chart, we have a carbon, we have a nitrogen, we have an oxygen, and then there's fluorine and all this kind of stuff. So in the periodic chart. And then here's neon, I believe, our noble gas. So what we find is neon already has its 8 electrons, fluorine has 7 in its outer shell, oxygen has 6, nitrogen has 5, carbon has 4. Okay? So now then oxygen has to be plus 2 electrons, right? To look like neon. What about carbon? Carbon has to be plus 4 electrons to look like neon. What about hydrogen? Because hydrogen's over here and then helium's over here, right? So hydrogen has to be plus 1 electron to look like what it needs to look like. And we have 2 of these, right? So now then, how do we draw out what this structure looks like? All of these are nonmetals. Hydrogen's considered kind of this weird hybrid. It can be a nonmetal, it can be a metal. It just kind of depends how you classify it. So what you do is you take the thing that's in the middle, the thing that needs the most needy atom, and you throw it down in the middle. And then you put everything else around it. So I'll put an oxygen up here, I'll put a hydrogen here, and I'll put a hydrogen here. So now then, what do we do? Well, that's kind of interesting. There's a little trick that you can do. I'm going to call this NAS. So N is what's needed. A is what's available. S is what's shared. What this allows you to do is to figure out how these things, this hydrogen, carbon, and oxygen, can be associated one with another. This is really, really, really good for covalent compounds. So I know I have one carbon, I have one oxygen, and I have two hydrogens, okay? So now then I'm setting up a neat little table here, right? Okay. So how many electrons does a carbon need to have? Do you remember that thing called the octet rule? Right. It needs 8 electrons, and there's one carbon, so 1 times 8. What does oxygen need? It also needs 8 electrons. What does hydrogen need? Hydrogen's a little different. Hydrogen, the closest noble gas to hydrogen is helium, which means it needs 2 electrons, and we have 2 hydrogens. So if we take these things and we add them all together, what do we get? 8 plus 8 plus 4 is 20. Is that right? 8, 8, and 4, 20. What's available? Carbon, because it's in a thing called group 4 or group 14, only has 4 electrons available. What about oxygen? It's in group 6, so it has 6 electrons available, and there's one of them. Hydrogen is in group 1, so it only has 1 electron available, but there's 2 of them, okay? So 4 plus 6 is 10, plus 2 is 12. Did I do that right? 4 plus, yep. So I have 20 and I've got 12. To get the shared, this is what you do. You subtract the available from what's needed, and you get 8. So you have to have 8 shared electrons. And if you'll recall, a shared electron, if you put 2 of them in close proximity, we call that a bond. So if you take these 8 shared electrons and you divide it by 2, that's going to equal to 4 bonds. So how do I set up 4 bonds whenever I only have 3 things? Well, it's fairly straightforward. You put 1 bond here, and 1 bond here, and 1 bond here. So now then I have 3 bonds that are working on forming this formaldehyde. How many electrons does hydrogen need? 2. How many are right here in this 1 bond right there? 2. So these hydrogens are perfectly okay. So if those hydrogens are perfectly okay, let's go ahead and I'm going to check them off. That doesn't look like much of a check, so let me go ahead and change that out. Good job, hydrogens, you did your job. How many electrons does carbon need around it? It needs 8, right? Remember, carbon needs 8 electrons. So does oxygen. Well, let's deal with the carbon first. So what if we put a 4th bond right here? Okay, so that looks kind of weird. It's called a double bond. So they're in close proximity to one another, but they're, it's kind of like holding 2 hands of someone at the same time, okay? They have 2 hands, you have 2 hands, you hold the hands, and you got a double bond, okay? So that's interesting. So now then, if I look at this, I find that I have 1 bond here with hydrogen, one bond here with this hydrogen, so that's 2, 4, 6, 8. So that carbon now is okay. I've got enough things to allow for 8 electrons there. That's awesome. But what do I do with anything else? So carbon's good, hydrogens are good. What about the oxygen? Well, what we do is we look back at how many electrons do we actually have available, okay? We look back at this right here. We have 12 available electrons, and currently we only have 8 that are showing. So what we do is we take the other 4 electrons and we go and we put them right next to that oxygen. And they always are in pairs because it's awkward to dance by yourself. It's always better to have a partner. And they always make you look better, right? And so now then, whenever I'm looking at this, I have 4 dots around that oxygen and 2 bonds. Each bond is worth 2 dots. So now then, as a result, I have 8 electrons around that oxygen. And I have a completed formula for formaldehyde, which is a covalent compound or a molecule. Now, these covalent bonds are directional. That's kind of interesting. So I liken this to a handshake. You've already heard me say this. So a handshake is something where you shake someone's hand, and if you're a guy shaking another guy's hand, you kind of grip the hand fairly firmly. What you're trying to do at this stage is to kind of assert your presence. Now, this assertion of presence doesn't mean that you're more manly or anything else like that. It's just something that guys do. We're inherently competitive in that regard. So, but one of the things that some guys do, and I've been privy to this a number of times, is what they'll do is they'll shake your hand, and while they're shaking your hand, they'll actually pull your hand toward them. That's that directional component. When you have a handshake that's pulled towards you. It's a weird, awkward thing, but some folks do this. So what happens is, in the case of, say, water, where we have an H bonded to an O bonded to another H, what we have is oxygen is bigger. Okay? So with oxygen being bigger, it's stronger. And because it's stronger, it pulls electrons towards it. It pulls the handshake towards it. So now then, what happens is, because it pulls that electron toward it, the hydrogen becomes a little bit positively charged. So I'll put a plus over here on the other side of the arrow. So now then, what happens is, we've got a polarized bond. It's an unequal sharing. Hydrogen smaller, it's weaker, it's whatever. So oxygen wins. It kind of grabs hold of its lunch money, hydrogen's lunch money a little bit more. But they're actually sharing. And so now then, what we find is this hydrogen becomes delta positive, as does this hydrogen. That delta, that little funky S with the circle at the bottom, that's the Greek delta. That means oxygen becomes delta negative. So now then, this directional covalent bond plays an interesting role. So if we're looking at water, and we're looking at how this works, we start to see that now then, water, which has a negative charge, can kind of be close to something called, let's do it in this color, okay? An Na+. You see that? Hydrogen, because it's negatively charged, can be close to Cl-. And so because of these pluses and minuses in their charge, they are able to dissolve ionic compounds. Water can dissolve ionic compounds. Now, the structure of water isn't quite like this. So let me go ahead and correct that structure real quick. The structure of water looks more like this, where we have an oxygen here, get those lone pairs there, and a hydrogen here, and a hydrogen here. So as a result, we kind of have this bent form. And this bent form here allows for something interesting to happen. So you still have this pull toward the oxygen. This is delta plus, this is delta minus, this is delta plus. But now then, because they're kind of pulling in the same direction, what we have is a larger pull this way. So the oxygen can kind of pull those hydrogens along. The way I showed it over in the pink, it's kind of there's no pull. It's just kind of I'm going to pull it to myself, whatever. But realistically, oxygen kind of pulls the hydrogens along. Kind of like you would a couple of siblings who are holding onto your legs. And you needed to go somewhere. Now, with this, we find that we have what's called a polar molecule. So it's not ionic. It has a polar end and a polar, a positive side and a negative side, but they're not fully positive and they're not fully negative. They're just polarized. Okay? Whereas if we have something that kind of looks like carbon dioxide, which is a greenhouse gas, carbon's here, oxygen's here, it looks like this. Oxygen has a greater pull than carbon, so it's pulling this way. So this is delta plus, this is delta minus, this is delta minus. Now then, as a result, it becomes non-polar. This is a non-polar molecule because there isn't a clear winner as to what side's plus and what side's minus. There's not a plus side of the molecule or a minus side. It's like a tug of war that is equally balanced. No one wins. It's non-polar. Now, when we start looking at these formulas, there's lots of ways that you can represent formulas. C6H6 is a better way to represent a formula than just CH, because a CH is just a CH like this. Does that make much sense? Nope, because remember, this carbon right here has to have 8 electrons around it. So you have to make sure that you do things right. That is where that NAS method really comes into play quite nicely. And you can do it for any covalent compound. So now then we can start to look at a couple of different things in terms of how this looks. We've already looked at formaldehyde, and we know that there's a couple of lone pairs on this oxygen. So we've got 8 electrons around the oxygen, we have 8 electrons around the carbon, and we have 2 hydrogens, each with 2 electrons. For glutaraldehyde, another common embalming fluid, those oxygens have to have the same thing. But if you look at this, we can confirm this octet rule, can't we? Because now then, we see that each carbon has 4 bonds. And because each carbon has 4 bonds, we know that that means it has 8 electrons. And if it has 8 electrons, then that means this thing and this thing and this thing and this thing and this thing are all in good shape. Those 2 oxygens are in good shape. And each of those hydrogens have just 2 electrons. So that works well also. So we can start to use some of these things to these Lewis dot structures and how everything kind of sticks one to another to see how they will play out. So going back to the polarity, we know that oxygen, and I said it was because they were bigger. Let me correct myself here. We have something called electronegativity. Electronegativity, with the exception of the noble gases, which I'm going to say don't care about those in terms of electronegativity, okay? So fluorine's right here, okay? Francium's here. Electronegativity increases as you go from bottom left to top right. So oxygen's up here by fluorine. So we know that carbon is less electronegative than oxygen, and carbon and hydrogen are about equal, okay? So we know that this carbon is a little bit positive and this oxygen is a little bit negative. So when we're doing embalming and we've got this protein that has an NH2, and I've got this nitrogen that has a couple of electrons, and it's delta minus, what is this delta minus nitrogen going to react with formaldehyde? It's going to react with the delta positive, see that delta positive right there? Carbon. So this thing's going to react right here. Likewise, because it's delta minus, and for glutaraldehyde, it has a similar structure, this thing is going to react right here. So we can start to predict how things will react because of its structure. This is critical for all things chemistry. Now, we also have molecular mass, which we've talked about, so make sure you refer to that, and formula mass from a formula unit. But I want you to make sure that you understand this thing called polarity, and I want you to understand how to do the NAS, because that will allow you to determine what happens with molecules and compounds, and it will really make your life easier in the long run.